see you're all here. I guess it's a hot topic. Let's start. Is there anybody here who competed in the 1 billion row challenge? Nobody? I did. So let's start the scene. This was New Year's Eve. Had a great time. And for the last, I don't know what it is, like 30 days, I've been programming every day with the advent of code. Anybody who competed in the advent of code? More. Great. So I was already used to waking up each morning, doing some competitive programming, making a problem, fixing this problem. And I was afraid, January, I would have nothing to do. So I woke up, 1st of January, a little bit of a hangover. And this tweet dropped from Gunnar, the 1 billion row challenge. How fast can you aggregate 1 billion rows using modern Java? And modern Java is vanilla Java. Sounds interesting. Let's try. So what is this challenge? How fast can you parse a file with 1 billion rows and print the results? And you're just allowed to use vanilla Java. So no Spring Boot, no big data, libraries, nothing. You get one Java file, everything you do inside that file. Sounds interesting. So these billion rows, these billion records, they look like this. First you have the name of a station, which is a city. Then you have this semicolon. And then there's a value, which is a temperature. Right here is now 30 or something. The station name is 1 to 100 characters. The temperature is from minus 99.9 to what it is right here, 99.9. And each row is separated by a new line. This is an example. So you have Hamburg, 12 degrees, etc. 1 billion rows. And in the end, you need to output the following. You need to output the name, so each unique name, the min temperature, the average temperature, and the maximum temperature. Sounds easy enough, right? We just go through 1 billion rows, remember the names, remember the min, the max, and the average. You can't really remember, you need to calculate the average, and then you print it out. And the output format is actually pretty weird. It has to look like this. You start with this curly bracket, then the name, and then this. Not a coincidence, because this is actually what a Java list outputs. If you have a list, you output it, looks like this. The input, the middle part is the toString function. That's the challenge. Couldn't be that hard, right? Gunnar also provided us with a baseline implementation. Great. He used files.lines to read all lines, which is single-threaded. Possible optimization there. And he uses streams to collect the results. And his entire application runs through 1 billion rows in just under 5 minutes. Good. Let's look at his code. So the first thing you see is there's like this result row, which prints out the min, the mean, and the maximum temperature. And there's a little rounding because we don't need the entire double value. We need to just have one position after decimal point. What we also have is an aggregator. And this aggregator has the min and the max value. It has the entire sum of all the values combined and a count. And if you have a sum and a count, we know how to calculate an average. And this is the rest of the code. Looks a bit complicated, but let's go almost line by line. But we start at the bottom. We use file.lines, which basically gives us a stream of all the lines. That's one problem taken care of. And for each entry, we create a measurement where we split the line between the name and the actual value. And in the end, we collect them with a grouping by, and we pass in this collector. And this collector actually consists of two things. Every time you have a stream and you want to collect it, you need two things. The first one creates a new aggregator. So if you have this input, creates a new aggregator where it combines the double value. So it does mat.min with the min and the value, the max with the value. It adds the value to the sum and increases the count. The segregate aggregator is where you aggregate two aggregators together. And this basically means that this entire thing collapses into a unique set that we can use with the grouping by. And the grouping by in this case is the city name. There's again this rounding bit, and we print out the results. Pretty straightforward. And it's easy if we print out this map, which again is the format we saw before, we automatically get the correct thing. So I tweeted out back to Gunnar, sounds cool, I made something, let's submit and see. I was actually the first one that submitted the PR. And I had some small changes, and I already slashed like the runtime from 5 minutes to 2 minutes. And I was like really proud of myself, because 2 minutes, that's already way, way faster. And the fun thing about this entire contest is that it's open source. Like everybody could see each other's pull requests. If you go to the code, which is on GitHub, you could actually see the calculate average from everybody that competed. So my tricks, I already gave them away on the 1st of January, but luckily it didn't stop there. Everybody was looking at each other's code, learning, experimenting, and adopting their own ways, which was really cool to see. Turn off that phone. So what did I do? The first thing I did was, instead of file.lines, I added .parallel. So I wasn't using a single thread, but multiple threads. In my case, on my MacBook, 8 threads at the same time. 8 times faster, great. The second thing, instead of creating an array with strings by calling split, I actually looked at the pivot point of the index in the string and used a substring and a different substring to break the string in 2 pieces. Because why would you create an entire array when you just need to have these 2 strings? There were some other smart things. Because I was using .parallel, I couldn't use a regular map, but I needed to use a concurrent map. Otherwise, you run into concurrency issues. Didn't put a round thing beneath that. But in the end, I'm getting the entry set. I sort them because the result needs to be sorted. And I join everything together and I print it out. This was already like more than twice as fast, and I was pretty pleased. But if you look at my code 2 days later, a lot happened already. You can see all these things. I kept a change log of everything I changed. But the runtime was already going down from 2 minutes and 8 seconds to 23 seconds. How do you do that? How do you make this code even faster when it's already parallel? Let's look at some changes. This is Sir Jackie Stewart, Formula 1 racing driver, and he said, you don't have to be an engineer to be a racing driver, but you have to have mechanical sympathy. And in his case, he was talking about the car. You don't have to be an engineer to know exactly how the car works, but if you at least understand what is happening beneath the car, you probably get much more information, and you're much better at tweaking things and telling your engineer what to change. And this mechanical sympathy is also something we can apply to programming. If you know the hardware and if you know what's happening underneath, you can optimize for that. You don't have to be a CPU designer, but it's good to know what a CPU is made of. This is just an example of a CPU. Yours might look completely different, but some of the things are similar. So you can see a lot of stuff on the side. There's a memory controller, but basically it's a 4-core machine. So there's 4 cores, and each core has a little bit of memory that's very small and really fast. This is called the L1 memory. Every core also has, in this case, a second part of memory, which is bigger, but slower. But it allows you to store more information. And when you access it, it gets put into the L1 cache. And there's, in this case, also a shared L3 cache, where everything is initially. Before it's on your hard disk, then it gets loaded in the L3 cache, and then when a core accesses something, it goes L2, L1. Ideally, you want everything in the L1 cache. It's the fastest one. But yeah, it's very small. You can't put everything there. And if you put stuff there that you don't need, that's just waste. So that's what we want to try to do. We want to put the information in a smart way into this L1 cache and process everything. Here you can see like a comparison in times. If you, again, these times will vary for every CPU, just an example, but the order of magnitude is pretty understandable. If you just have the register in the CPU, it's very fast, like 0.3 nanoseconds. And if you have to load something from the L1 cache, it's 1 nanosecond. Still very fast. But you can already see if your data isn't in this L1 cache, but you need to go to the L2 cache, it's 3 times slower. It's 3 nanoseconds. And if it needs to load it from the L3 cache, it's already 13 nanoseconds. And this snowballs. Like if you go all the way to your solid state drive, it's about 0.1 millisecond. So that's our goal. We need to optimize for this architecture. Even better, you need to optimize for the architecture that the actual contest is running on, which in this case is a cloud server somewhere. I didn't do that. That's also why I lost all bits of hope in the last week, because every change I did was faster on my machine. Actually, I had the fastest program on my machine, works on my machine, but it became twice as slow on the target machine. And that's when things don't start to correlate anymore and things fall apart. I could rent a server, obviously, but I'm Dutch, I'm cheap. I didn't do that. One of the things we did, I did, but everybody did, was don't look at these double values as doubles. We're just having like one position in the after decimal, just multiply everything by 10, now it's an integer. Already way faster. Integer math is way faster for a CPU than floating point math. Just use integers. Easy. Second thing is a different way to segment the file. So initially we had the file.lines and we called .parallel, which is great. It divides our work into all the registers or all the cores. But the first entry in the string gets to core 1, the second entry goes to core 2, and that piece of information gets loaded in all the L2 and L1 caches. So if you do that, probably the L1 caches of all the cores have seen all the data, which is a bit of a waste. It's better if you break this file into segments, like the first, of these billion records, the entire file is like 13 gigabytes. So I've got 8 cores. So let's say, I don't know, 1.5 gigabytes for the first core, 1.5 gigabytes for the second core, etc. Now, every time you load something into the L3, L2, and L1 cache, all of it is processed by this core. So that's already way faster because you go like first row, second row, and it's already there. You don't need to reload it. So this simple change, we're still doing the processing in parallel, but this simple change by just assigning a piece of the file to a separate core, way faster. So in this case, what we do is we look at available processors. That's what we need to divide it by. And then we say, this is the entire segment. This part is for core 1, this part is for core 2, etc. Again, way faster because all the data is correctly loaded in the cache of the CPU that you're optimizing for. One of the biggest optimizations actually was memory mapped files. Who here has heard about memory mapped files? I had never heard about memory mapped files. What you can do, you can say files there's probably, yeah. You can say files.new byte channel, gives you a byte channel for a specific file. And this entire file, your kernel or your operating system maps this directly to memory. So you can just say memory address, this is part of my file now. So we say file channel.map, and we say we read only because we're not writing, and we get a byte buffer. And this byte buffer basically says this is the file, and this is now in memory, and you can access it. And again, we can process that, all the segments in parallel. So each of these segments gets a core, and it just goes through it. Way faster than using a buffered reader, for example. This is also the point that I mentioned byte buffers. Byte buffers are great for reading data. They are the future. If you want to do something with this, go for byte buffers. They're perfect. But we want every last piece of speed. We want unsafe. I'd never used unsafe, but it's awesome. If you're a C developer, I was a C developer before, you can just direct memory access. You can just peek and poke around every memory address. You can read, you can write. Now you're a string, now you're long. I want this piece to be a long value. I want this piece to be an int value. Perfect. But it isn't called unsafe for a reason. Java also wants you to move away from this. Don't use it in any production code unless you really have to. But if you really have to, contact the guys at Oracle, because there's apparently something they still need to implement. But it's just a little bit faster because there are no bound checks, etc., etc., etc. Byte buffers will still have boundary checks, and but I don't care about boundaries. I don't care about unsafe. I just want raw speed. For me, it was the first time using it. How do you use unsafe? Well, you need to get the unsafe. How do you do that? Is there a line? No, there's not. You load the unsafe class, you get the unsafe, which is a field. You set it to accessible true. Now we can access it. And then we load it into a private static final field. And now we have our unsafe. And using this unsafe, we can say, I want to go to this memory address, and I want to read this value, etc. So in my case, I did the same memory mapped files. I said file channel.map, and then I called .address. Basically just a long value. This is the address where the data of the file is now accessible to you. Your kernel does the rest. And now you can do stuff like unsafe get byte at this address, reads the first byte of the file. Perfect. If you did map address -1, who knows where you end up? Probably crashes your machine. So you need to take care. Then somebody on the internet told me, you have to use SWAR. I had no idea what it was. But I was, at this point, processing byte by byte, each character, finding the separator, doing that kind of stuff. But I found out that using SWAR, you can do 8 at a time, which is perfect. SWAR actually stands for simped as a register, which still doesn't help you because simped, what the heck is that? That's the single instruction, multiple data. That's the actual instruction that your CPU is executing. Again, doesn't make sense yet. Let's look at an example. So this is part of the string. We've got Tokyo, where it's -18.3, and in Amsterdam, it's 31.2. We can actually read the first 8 bytes into a single long value. That fits, because a long value is 64 bits, and the byte is 8 bits. And because little endian, big endian, the thing we read is actually in reverse if you look at the hexadecimal code. So it's Tokyo delimiter -1. We can read this in a single go using unsafe, give me the long value, which is really fast. But what I want to do is find the delimiter. Now we create a mask. The delimiter that we're looking for is this semicolon. And we just create a mask with 8 bytes of the thing that we want, which is 3B, 3B, 3B. And you can already see it's here. Like, I know where it is, but we have to tell the computer, look for that thing. But we don't want to have a loop. We don't want to go byte by byte. We want to do this in a single go. How do you do that? Turns out this code does that. Looks intimidating, but let's break it down. So what do we have here? We have the top row is actually the long value of the data we've been reading. And the second line is the 3b, 3b, 3b. That's the delimiter, like 8 times. If we XOR these things together, you can see that there are no differences in this byte. So it's all zeros. That's perfect. We found what we're looking for. But yeah, there's so much junk left, it's pretty useless. Now, if we subtract this magic number, which is basically just the least significant bit 8 times, we get a different value. And now it's all ones. Because all zeros get turned into all ones, and there's actually an overflow bit in the first location. But remember, the only way to get all ones if it's initially all zeros. That's the important thing. So now we have these two values, and we AND them together with the inverse of the thing we're looking for. The thing we're looking for, all ones, the match, all ones. And we get this number. We AND them together. Basically, it keeps the initial ones. So here there was just a single one, or with the match, there was all zeros. So this was the single zero. There was 1 0. This one was all zeros. And you can see the only way to get all ones in this situation if initially it had all zeros, if there was a match. Now, if we AND this together with the most significant bit, the only way to get this one to be 1 is if initially the match was all zeros. So we get just this single value. We've isolated the byte we're looking for. And what we do now is we count the number of trading zeros, which is 47. We need to divide this by 8. Because 8 bits per byte. Actually, dividing is a very costly operation, so it's better to shift. If you shift it 3 places, that's the same as dividing by 8. And you can actually see that we found the result. We found the delimiter. And we did this all for 8 bytes in one XOR operation, a minus, an AND and an inverse, and another AND, and a shift and trailing zeros. So that's maybe 7 or 8 instructions on a machine. And we've processed 8 bytes of data. We didn't have to loop. We didn't have to do anything. This is really fast. And this is also the moment I started to realize, if we are now parsing all this data long by long by long, why are we creating strings? We don't need to create strings while we're parsing this data. We just need to check if our long values are the same as a long value we've seen before. Only when we print it out, finally, we need to actually look at these strings. Other than that, why are we creating strings? We don't need to. So instead of allocating, storing, and comparing string values, we can just check these 8 bits in a single 8 bytes in a single go if you look at getLong and getLong, which again processes 8 bytes at the same time by comparing 2 longs together. Perfect. And this is also very close to branchless programming. So what we've just did was already branchless programming. There were no loops in the SWAR code. Why do we want branchless programming? So your CPU has a big pipeline of instructions. It wants to do all this work. And they work best if you fill this pipeline as predictably and fast as possible. So if you can tell the CPU exactly what you want to do in the future and fill this pipeline with everything you want to do, perfect. But what comes after an if statement? Or what comes after a switch statement? I don't know. That's something that's very hard to predict. So branches are always where this predictability breaks down. So if we can avoid that, if we can just fill this pipeline, we get amazing speed. And the CPU is able to arrange everything to do it in the best way possible. But if there's an if statement, things might break. So branches are the bottleneck. The absolute value. If you were asked to write the absolute value function, you might do something like this. If x is smaller than 0, then we return minus x, and otherwise return x. But again, if you call this method, and there's something beneath that, you can't just use this value x or predict that what's happening, because we don't know yet. This is a branch. You could also do this. You shift x 31 places in case of an int. So that means that the bit we're interested in is actually if it's negative or positive, that single one. We shift it all the way, and we shift using the double shift, where we shift in the sign bit. So if it was a positive number with a 0, we've got all zeros. And if it was a negative number with a 1 first, we get all ones. If we add this to our number and do XOR, we're done. If it's all zeros, we add 0 and we XOR with 0, nothing changes. If it was all ones, we add -1 and we XOR it with each other. Apparently, it gives you the negative of the number. No if statements. We can just fill this pipeline and continue because we already know what needs to be done way faster. So I was thinking about this, and I was actually the first one. I was still using this byte array input, which had all the strings in it, the entire file basically in it. I knew where my temperature was starting, and I knew where how long my temperature was. And I was really pleased with myself. This is the first branchless code I ever wrote. So what does it do? Again, this number will be 0 if positive and 1 if negative. And what I'm doing is I'm using this basically tiny part of the ASCII table. You can see that all the digits, 0 to 9, they have this fourth bit, fifth bit set as 1. The negative sign has 0 there. So there's this unique bit which we can use, which is perfect. So I'm shifting things 4 places, and I'm isolating that single bit, and I'm flipping it. So again, 0 if positive, 1 if the number that we eventually have is negative. Because at this point, I just have the bytes of the temperature. I don't want to do long.parse or double.parse string, because that's very, very slow. I want to do something faster. So the second thing is I check if the number is maybe 1.1 or minus 11.1. So the length can be 3 or 4 or even 5 if it's a negative number. So I can easily check this because I already knew the length, because I was using SWAR to find the next line. And then I did some calculations. So for the first digit, I just subtracted the character 0, which means that if it's 0, you get 0. If it's 1, you get 1, etc. I also did the same for the second and the third digit, if it's available. And then I had this calculation. You can actually see that I didn't subtract the 0 from these two, because these two will always be present. So I could actually subtract this number, 528, because that's 0 and 0 times 10. So that's an even better optimization. Oh, it actually says here. So 528 is 0 times 10 and 0. Because I always need to subtract those values, I can pre-calculate this single thing and save even more instructions. I was pretty pleased with this. I was like, yeah, it was faster, and nobody seemed to notice. It was my secret trick. And then this user Mary Kitty came along. And let's just look at his code. So what does this Mary Kitty do? Looks very intimidating. I had a hard time understanding it the first time, but let's go line by line. So the first thing he does is he reads this temperature in a single long value. I was still using a byte array, but he's just using get long, put everything in a single long value. So let's look at an example. Again, we've got this table, and for example, we're reading from minus 18.3, and then a new line, and then some junk. There's always some junk, because who knows what's behind our number. But we want to parse this string minus 18.3 into a number, an int. So the first lines of his code is reading the long value, inverting it, and then he kind of does the same thing where he counts the number of trailing zeros when you AND it together with the dot bits. These dot bits are 3 very specific locations. And you can actually see that's the same thing as, that's the same bit that's unique for the minus and the dot. And it can be in these 3 locations. It can be, can be in if it's 1.1, it's there. If it's 11.1, it's in the second spot. And if it's minus 11 or minus 18 point, then the dot is right there. So the result is either 12, 20, or 28. That's what we store. And in our case, it's 28 because we've got the largest number here. So his next trick, again using this unique bit, basically the same as the previous code, is finding the sign. This bit is unique, so he shifts it first 59 places that way, and then he shifts it 63 places that way. And this is the same as the branchless absolute value function. Now we get either 0 or all ones into this long which is signed. Now remember the number we had of the dot position? If we XOR it with this value, this is actually one small optimization I made, then you get either 16, 8, or 0. And that's the amount that we need to shift the number. Perfect. Now we isolate, or we create a mask. If there's a minus, we need to mask out some data. And now we isolate, using this 0f, 00f function, only this part of the digits. The rest becomes 0. So now we kind of have the things that we want. We've got all the ingredients. And our number is actually in this specific form, where we have the hundreds, the tens, and the units. So in our case, when it's minus 18.3, we actually have a 1 here, an 8 here, and a 3 here. So close. It's still not minus 18.3, but we're close. Turns out that if you have this number, this digits number, and you multiply it by 1, and you get this number, which is basically the same number. If you multiply it by 1000, it gets shifted. And if you multiply it with more zeros, it gets shifted even further. There's a way that we can get all 3 of them in the same column without any overlap. Interesting. It turns out, instead of doing this 3 times, you can even multiply it by this number, and you get, as a result, these 3 numbers added together. Interesting. So if we do this single calculation, we get 0c in that position, which is actually the same as 12, which is 3 and 8 and 1 together. Close. It's not what we want, but it's close. What we want to have is not 1, but this number needs to be multiplied by 10, and this number needs to be multiplied by 100. Turns out you can create this magic multiplier. You can see it at the top. It's basically the same thing we just did. And if we now look at this number, it has B7 in it, and B7 is actually 183. That's the number we were looking for. So using some crazy math where we were multiplying and shifting, I don't know how people come up with this. I was already really pleased with my branchless method, but this guy's crazy. And the last thing we do is basically the same thing as we did with the absolute value. We add it and we XOR it together to flip it if the thing is negative or not negative. And now we get minus 183, 10 times the double value that we needed. It's crazy that this works, but it works. It's actually pretty lucky because if it had just a little different layout, then you would get overflow, things would collide, and this trick wouldn't work. So, where are we now? We are using memory mapped files to read this entire file. into memory. Then we are using SWAR to find the delimiter and actually read part of the name of the string. We have this crazy branchless method to parse the temperature, and then we can go on to the next record. We still need to remember all these values to, in the end, print out what we know. We need to store everything. So initially, I was using a hashmap, and if you look at a hashmap, how it works, this is a hashmap of size 8, very small, and we want to store the string London, and we want to store the some temperature. So how do we do this? We take this string and we call .hashcode, which gives us an int value, which is, well, you would like this to be unique, but it will never be unique because a string can be larger than the amount of int values. So there might be collisions, but you get a semi-random number every time you put in a string. Now we just do mod 8, because we only have 8 spots in our hashmap, we get 3. Perfect, that's where we store London. Now we want to store a second value of London. Well, we do the same thing, same hash code. We get 3 again, and we update this record. Now it has 2 temperatures in it. Perfect. And now we want to store Rotterdam. Also, no problem. We get a different hash code. We do modulo 8. Oh, wait. That's also 3. Now, what do we do? If you look at the implementation of hashmap internally of Java, in case of a collision, it creates this tree-like structure where it just says, I'll just put it like, I'll turn that thing into a tree, and we first check if London is if Rotterdam is the same as London. No, it's not. Then I look at the next one. I look at the next one, the next one. But again, this hashmap, very fast, very safe, but we can do better. So I asked ChatGPT, how do I make this better? Or how can I make this faster? And GPT told me, have you looked at forward probing? I had never heard about forward probing. Basically, it means if you get 3 and the thing in 3 is not what we're looking for, just put it in the next one. And the next time you have London, well, London is there in 3. Next time you have Rotterdam, you look at London, no, it's not there. Just look at the next free one. So much simpler. And it's actually way faster than building an entire tree with data structures, etc. So I decided to write my own hashmap, and it's not really that long. We can go through it. So I'm actually building up the hash while I'm going. So I read this long value, which is part of the name of the string, and I update my hash. I don't want to do it afterwards because this is the moment that I have everything in memory. L1, we want to optimize this. So we update this int value while we go. Then we end it together with the table mask. This is the same as modulo, but I'm using, my table is always a power of 2, so I can just mask it faster. And I get the index. And now I look in my hash table, which is just an array. And if there's nothing, I insert it. So I create some byte array, and I fill my entry there. It's a new entry. Perfect. You might have already seen I'm not using any objects. I'm putting all my data into a byte array, but I'm not using these bytes. I'm just saying, this is my byte array. Put a long there, put an int there, put a byte there, and copy some memory of the name in there as well. This is just a little bit faster because it's more compact. Objects have some overhead. Maybe in the future, with the current way Java is going, this isn't even necessary. Turns out it isn't even necessary because Thomas, who eventually won the contest, he was using a regular object. But yeah, he's also the one who created the Graal VM. So yeah, that's tough competition. This is called the flyweight pattern, where you have just have data, you remember the indexes, and you just read it, just pure data. If the entry is not null, then we need to check if the entry is actually the same. And we, like I said, we are not comparing strings here. We're just looking at the long values. And now we update the entry. Updating the entry exactly the same way. We just read these ints and longs, and we put them in the correct spot. Perfect. Each core has their own hash map in my case. So You don't have to worry about collisions or any other stuff. We merge them in the end. And if the thing isn't, so it's not null, it's not the thing we're looking for, we just use index +1, we mask again, we go to the next one. Forward probing. Really fast. Like I said, Thomas, real genius, works at Oracle, and he kind of came up with Graal. And he said, well, it's getting ridiculous now. It turns out that when using memory mapped files in Linux, it actually takes quite a long time to unmap. So we're done with everything, but the kernel is still unmapping this file from memory. But we've already printed out the results. Can we do something about it? So he said, well, I have this solution. I need to check with Gunnar. Can we use this? Turns out Gunnar said, sure, go ahead. And everybody copied it, including myself. This is what he came up with. So our program starts. We've got our main program. And the only thing it does, it spawns a worker. And this worker is an entirely new process. And this is the process that's actually going to do the mapping, do the calculations, print the output, do the unmapping. What we do is we couple our main system out to that system out. So we've got this worker, which is doing the actual work, and our main program basically dead. Doesn't do anything, just copies out this stream, but it's already almost dead. And the moment this worker closes the stream, our program completes. Timing stops, we can say we've done a really good job, and then in the background, this worker starts unmapping, etc., etc. No longer part of the contest, not our problem. Crazy. Which JVM do we use? Initially, I was using the Oracle VM. I tried other VMs as well. I tried different vendors, different versions. Maybe 17 is faster than 21, who knows? But in the end, almost all the top entries used Graal native compilation. Because if you can do work before actually running your program, doesn't count. Perfect. Some people were using the new vector API, which is something Graal doesn't really support yet, or they're working on it. But this is where you can basically vectorize operations, where you can basically the same thing we were doing with SWAR, but then using an API in Java itself. But most top entries were using native compilation. Well, how do you do that? Well, it turns out it's actually pretty simple. This whole project was built around SDKman. If you're not using SDKman, please start using it. It's the best way to get Java on your machine and switch between versions, especially if you do the work that I do, consulting, where you have for each project your own specific Java version. You just type in a command and the correct Java version gets loaded. In our case, 21.0.2 of Graal. Actually, we all started with 21.0.1. Thomas noticed some things were wrong. He quickly built a new version of Graal, especially for the competition. Like I said, I'm not going to win this thing. I might get far, but I'm not going to win it. And then we give it some extra options. So one of the cool things is I'm unlocking experimental VM options, and I'm using this GC, the epsilon GC. Who knows what the epsilon GC does? Exactly. It does absolutely nothing. It just ignores everything. Doesn't clean up anything until your program exits. Perfect in my case, because I'm not making a mess. I'm fully in control of everything I create, and everything I create I'm using. So I don't want this garbage collector to do stuff. We set some optimizations, heap size, some flags I just tried that they were faster and I have no idea what they do. That's how you optimize stuff. And then you call the native image command. Native image command creates an executable, and this executable is already pre-compiled, optimized, especially for your machine, prints out the result. This is what it looks like. First, we set the correct version, then it goes through a lot of stuff. This takes quite a while. It's becoming way, way faster. This used to take like 10 minutes. Now it's just a couple of seconds. Yeah, and in the end, you get an executable made specifically for your machine, and you run it, and everything's fine. We've got 4 minutes left. It's the final day of the contest. This is my entire changelog. So let's see how these optimizations did. So my initial submission, which was 2 minutes something on the target machine, on my own laptop, like these are the times of my own MacBook, 62,000 milliseconds. So then using a chunked reader, already way faster, I optimized the parser, created my first branchless method, already faster, 11,000 milliseconds. Memory map files, which you've just seen, slashes it in 2 again, not creating strings, takes it to 4,000, creating my own hashmap, just a little bit faster, but that allowed me to do other optimizations in a later stage. Adding SWAR for token checks, again, skipping more string creations. What else? Segmenting the files. Not using SWAR for the end of line, because if you parse the temperature, you already know where the end of the line is. So we were basically doing that double, etc., etc. Various tweaks for Linux caching, etc. I also like this one, where I went through my entire code and added a lot of comments. That's priceless. But that was really important. This whole thing was a community effort, and everybody was reading each other's code and optimizing and finding new tricks and trying out stuff. Really cool. In the end, I also switched MacBooks. I went back to my old x86 MacBook because I was able to use the perf command on that, which I cannot do on my MacBook. The perf command records the actual instructions that your CPU is being executing. So you can do really low-level optimizations. I had never used this tool, but Thomas was using it, so I had to use it as well. But again, things didn't quite correlate. So if it was faster on my machine, it might have been slower on the target machine. And that's where you lose, basically. In the end, 1 billion rows, Thomas, and he also mentioned all the people he stole, well, most of the people he stole code from, he did it in 1.5 seconds, under 2 seconds. I came in 7th with 2.1 seconds, so ignore the title of this talk. But again, on my MacBook, it was way below 2 seconds, so it counts. Like I said, initially almost 5 minutes, down to 2 seconds. This just shows you how much room there is in even simple applications. I want to thank Gunnar. He completely underestimated the effort it took to run such a contest. Like, everybody was submitting dozens of pull requests every day that he needed to review and check, and he needed to... people were, for example, skipping string checks because every city name was unique already. So people started skipping that, but he said, well, no, that's not allowed. You need to actually check that a string is the same in the hash map, etc., etc. So he might do another contest next year. So if you're done with Advent of Code, celebrate New Year's Eve, do the whatever comes next year. I really hope he does. We've got 0 minutes left. So if you've got any questions, come down here, ask them personally, and applause now. Thank you.